In this video, let's study one example of randomized block design. In the previous exercise, we studied completely randomized design. In this case, we use a robot to hit 40 balls and 4 different brands, 10 balls per brand. Here, we are not going to use a robot. We are going to use golfer. We are going to introduce in our results the distance that each ball reach. We are going to introduce more variability due to the technique and the experience of each golfer. This design is a little different. The objective to do a block design is, the main objective is to reduce the effect of the variability of all different golfers when they hit those balls. In this problem, we want to study how the distance that each ball reach is affected only by the brand. We try to minimize the effect of any other factor that could affect the distance that each ball reach. When we use the robot, actually the robot minimizes the other factors. But here we have to use different golfers. Refers to the example 10.7, suppose the randomized block design of part B is employed. Utilizing a random sample of 10 golfers, with each golfer using a driver to hit 4 balls, one of each brand in a random sequence. This is very, very important. Set up a test of the research hypothesis that the brand means distance differ. Use alpha 0.05. And in part B, the data for the experiment is given in the table 10.8 below. Use statistical software to analyze the data and conduct the test set up in part A. Okay, the data is given here in this table. The design of this experiment is like this. We are going to use different golfers, 10 golfers. Each golfer will hit 4 balls. All of these 4 balls will be from different brands. And the order in which all of these balls will be hit, the order is also random. There is a random order to minimize the effect of other factors in the distance. Remember, the first thing that you have to do in all of this problem is to do this problem using technology. How can you use technology? You have to go to StatCrunch. The original data is this one. When we send, the original data is given here, because this software requests that all my response variable must be in one column like this, only one column. Then we need to order this data using only one column. But for example, this value 202.4, we need to specify that correspond to the golfers number 1 and the brand A. That is very important to organize the data in this way, because this software in Stat, we have to click Stat and Nova. In this case, because we introduce a block design, we have to use two-way. Then my response variable is located in distance. That is the variable that we want to study. We want to study the means of all of these brands. My row column will be my block, golfers. And my column factor will be brands. Actually, this is the factor that we want to study. To do block design, you need to select these 3 boxes. Display means, because after that we need to do a comparison using Tukey or using Benferroni, but we need the means for each brand. We need to select this one, fit additive model, because when we select additive model, we don't take in consideration the interaction between blocks and brands. The effect of the brand and golfer will be added to obtain a distance of the ball. But there is no interaction between golfer and brand. There is no any relationship between golfer and brand that could affect the distance. Let's compute also Tukey to compare all means, and click compute. When we do that, we obtain all of these results. We have a ANOVA table here. This is ANOVA table. This is ANOVA table. And that is all means. That mean is for each brand. And here we have a Tukey comparison. The two key comparison could be done respect to block and respect to brand, but we are interested in brand because block is not studying this problem as another factor. We minimize with this factor in this exercise, and two key will be in this section. Okay, let's return to our PowerPoint, and in the PowerPoint we have this information. This is the ANOVA table, and this is the means for all brands, and here all blocks. That is the two key comparison for brands only. How can we show our work? How can we obtain all of these values in my ANOVA table? This is the ANOVA table. How can we use formulas and tables to obtain all of these results? Let's do it using Excel. We can send my data to Excel also. Then when we have my data in Excel, I can obtain all of this sum. We don't need to find here the mean because we use a shortcut formula. Then we need only the sum of each row and each column. For example, if we go to Excel, the way to obtain the sum is here. We need to input sum of all of this value in this column, and we need to copy all of this formula in all of these column, and we can do the same for rows. We need to obtain the sum for each row, these four values, and we copy this formula in all of these cells. Perfect. Then also we can obtain the sum of all values in this way, equal the sum, open parenthesis, all value from here to here. And also we can obtain the sum of all square value because we need it in our shortcut formula. How can we obtain the sum of all square value? Remember, the square is equal this value raised to the second power, and that is the square of the first value. We can copy this formula in all of these cells, and we can copy this column in these other three columns, and we have the square of all value. How can we obtain the sum of all square? Then it's very simple. It's equal the sum of all value from this cell to this other cell, and equal. This is the sum of all square value. We're going to need these two values in our shortcut formula. In the same way, we're going to use this sum of each column and the sum of each row in our formula. Let's return. But we did it already. That is all the information that we need. That is the table that we need to complete. Let's find the correction factor, this total sum of a square. The shortcut formula, we need to sum all square value and subtract the correction factor. Then we did it already. We already have the sum of all square value, and the correction factor is given by the sum of all value here, square divided by 4. The sum of the total square is 15,919. We need to write this value here, the total sum of a square. The degree of freedom, because we use 40 values and we use one mean, the overall mean, the degree of freedom should be 40 minus 1. In this case, 39. We need to write the degree of freedom here, 39. Then let's compute the sum of a square treatment. That is the shortcut formula, and let's substitute in this formula all sums, and in this case B will be the number of golfers that corresponds to the all value that we have to add for brand A. And when we do all of these operations, the sum of a square for treatment is 3,298. And the degree of freedom in this case, because we use only basically 4 values and one mean, the overall mean, then the degree of freedom for treatment will be 4 minus 1, which is equal 3. The sum of a square due to block, then we have to do the same thing that we did with treatment. The formula should be similar to the sum of a square treatment, but in this case we are going to use instead the sum of each column, the sum of each row, because the first block is my first golfer. The first golfer hit 4 balls. Each ball have a different brand.
This is my first block, my first golfer. All balls that this golfer struck were approximately under the same condition. Remember, in the previous problem we used a robot to strike all balls. The objective is minimize the effect of any other factor except the brand of the ball. However, we can identify the effect of each golfer using a block design. But here we are not interested in the difference between golfer. We are going to do that in the next section.
Then the shortcut formula is very similar to the previous one, where B1 represents the sum of all of these values in these rows. Is the first sum. This is B1. We need to square this sum and divide it by 4 in this case.
Because for each golfer or block, we have 4 ball or 4 brand.
When we substitute all of this sum here in those formula and divide it by 4 and we compute all of this operation, the sum of the square for due to block is 12,072.882. And what is the degree of freedom here?
The sum of the square for block measured the variation of the mean of each golfer respect to the overall mean. In the same way that the sum of the square for treatment measured the variation of the mean of each treatment respect to the overall mean. Then for the sum of a square block, we have 10 mean compared with the overall mean. Then the degree of freedom is 10 value minus 1 equals 9 degree of freedom.
Then the sum of a square error is the variability due to other factors different from brand and golfer. Then in this sum of a square error, we condense the effect of other factor, the effect in the variability of the distance for other factors.
Remember, the total sum of a square measures the variation of all measurement respect to the overall mean. In a randomized block design, we consider 3 sources of variation. The variation respect to the treatment, in this case the brand of the ball, the variation respect to the block, in this case the golfer, and the variation due to any other factor, in this case could be the wind, could be the temperature, or any other condition. Then the total sum of a square is equal the sum of a square due to treatment plus the sum of a square due to blocks plus the sum of a square due to error. Then we can isolate the sum of a square error subtracting the sum of a square treatment and the sum of a square for block from the total sum of a square.
Then we substitute all of this value in this formula to obtain the sum of a square error.
The degree of freedom for the sum of a square error is obtained when we multiply the number of treatment minus 1 times the number of block minus 1. Remember, the sum of a square error measures the variation of all measurement respect to the overall mean, but when we take in consideration on each measurement the mean of the treatment simultaneously with the mean of the block. For the reason we need to multiply k minus 1 times b minus 1 to obtain all possible combinations.
We can obtain also this 27 subtracting from 39 the degree of freedom for golfers and brand. When we subtract from 39, 9 and 3, we obtain 27. It's another way to obtain the degree of freedom for error. And let's continue with the mean square treatment. Actually, this is the variance due to treatment, the variability. We use the variance to measure variability due to treatment. This mean of a square treatment is obtained dividing the sum of a square treatment by the degree of freedom for treatment. This value here will be obtained dividing this sum of a square by the degree of freedom. And this value is 1099. Then the mean of square for golfer, we need to write this value in this position due to blocks, will be obtained dividing the sum of a square by the corresponding degree of freedom. Okay, that is the mean of square error, Mean of square error here is the sum of square divided by the degree of freedom. And the mean square block is the sum of square for block divided by the degree of freedom for block. Oh, I I make a mistake here. This formula is wrong. The degree of freedom here is 9, and actually will be b minus 1. Is the total number of blocks minus 1. We have 10 blocks minus 1 is 9 to obtain this result. Is 1,341. We need to test the hypothesis that all means, the mean distance reached for each brand, are equal. We are going to use this assumption. Then to test this hypothesis, we need to obtain the quotient for the mean square treatment divided by mean square error. This is the statistic that we are going to use to test the hypothesis if there is any difference between treatment. And this statistic, when we divide the mean of a square treatment, this value, by the mean of a square error, we obtain the F statistic that we have to write here, 54. Also, we can test the hypothesis that there is no difference between blocks. By common sense, we know that if blocks represent different golfers, then the distance that each ball will reach will be affected by the golfer. That is no surprise when we obtain the quotient between the sum of squares due to block divided by the sum of squares due to other factors. Error is a big number. These two big numbers indicate that we need to reject the assumption that there is no difference. Actually, there is a difference. And the p-value is given in the ANOVA table. The probability value or p-value of this big statistic is 0, as you can verify in this printout. Later, we are going to obtain the p-value manually using tables. And how can we obtain our rejection region? The test statistic that is this mean square for treatment divided by mean square error to test the hypothesis that all means for all brands are different, and this other test statistic is used the mean of a square due to blocks divided by the mean of square error. This statistic is used to test the hypothesis that all brands are equal. And this other test the hypothesis that all blocks, the mean of all blocks are equal. Our expectation have this distribution. This quotient, all possible quotient that we can obtain have this F distribution. We expect that 95% of all quotient are located in this area, and we need to find this critical value. How can we find this critical value using table? Remember, the degree of freedom of numerator here for treatment was 3, and the degree of freedom for the denominator is 27. Then we need to find these 2 degrees of freedom in this table, 27 degrees of freedom in the denominator, and 3 degrees of freedom of numerator. In the intersection of these 2 columns, we have the critical value. This is our value of reference that we are going to use to compare the result. Then let's write step by step all of this reasoning. First, we want to test whether the data in the table 10.8 provides sufficient evidence to conclude that brand means distance differ. Denoting the population mean of the each brand by UY, we test that the null hypothesis is always no difference, no change. Then all means for all brands are equal. Then the alternative is the opposite, the negation of this. Then at least one is different to the other, or at least 2 of them are different. That is the null and the alternative. And the test statistic I told you is F, the quotient for mean square. We did it already. The rejection region must be obtained using the F table. If we obtain the F value greater than my reference value obtained in my table for this level of significance, 0.05, this is the degree of freedom 3, numerator, the degree of freedom of the denominator is 27, and we obtain this value 2.96 in the F table for this significant level 0.05. Remember, we have different tables for different significant level, 0.05, 0.01, 0.10, 0.025. Because my evidence, my sample is condensed in this evidence fall far away from my expectation, because we expected 95% of all value below this F value. then if I obtain 54, we have enough evidence to reject the assumption that all means are equal. Remember, our expectation follow this distribution, and 2 point is here, and 54 was located far away from my expectation. Most of the value, 95% of the value, will obtain a value smaller than 2 point to 96, smaller than 3. This value reject the assumption because this distribution is obtained when we assume that all means are equal. This is a tricky comparison. We have to do a comparison from all brands using the same procedure that I explained in the previous problem. We have to use here this confidence interval to determine what is the difference between A and B. In this case, because it's negative, the second value is bigger. Here, because the confidence interval is between two negative values, that the difference between A and C is negative, is at least negative 24, but no bigger than negative 12, then the second value is bigger than the first one, and so on. And after that, we can order all of these means. In this 6 comparison, all of them will be strictly greater or smaller. Then all means are different according to this result, but you have to do it using the formal procedure. Let's stop here.